Hello, I'm Jonathan Aldrich. To understand how to implement programming languages, we need to understand the architecture of the machines we targeted. So let's put on our architecture hats and try to understand more about this topic. We'll start by discussing the memory hierarchy. But first, let's talk about why understanding architecture is important for writing compilers. The instruction set architecture of processors is the common target for compilers. We could target sometimes bytecode, but often it's the assembly language of a processor. Producing high-quality code requires understanding the hierarchical organization of memory, the format of data in memory, and the instructions that are used to manipulate that data. Finally, historical trends in computer architecture inform our compiler design and affect how we optimize code. Looking at the memory hierarchy, memory typically consists of a numbered sequence of 8-bit bytes. The address size limits the number of bytes that are addressable on a given machine. For example, a 32-bit machine can access 4 gigabytes of memory, or 2 to the 32 bytes. A 64-bit machine, on the other hand, can in principle address 4 billion times as much. Now that's more storage than has ever been created in the world. So it's more than we actually need, but it's nice to know we can access as much as we want. Unfortunately, of course, accessing all that memory is not equally as expensive. Memory that is further from the processor is slower to access. And so only a small amount of memory, such as registers and caches, can fit on the processor itself. For other memory, we have to go to other chips, or even perhaps across a network connection. So the memory hierarchy places things that are close that are used more often. Let's have a look at the memory hierarchy in more depth. It starts out with registers, which are on the processor itself, and they're accessible within a single clock cycle. The L1 cache would be associated with each processing unit, and accessing data there might take 2 to 4 cycles, as of approximately 2023. Main memory, on the other hand, requires going through a bus or other communication channel and will be consequently slower. Beyond memory, we might store data on a flash solid-state device, which would take considerably longer than accessing the memory. And then we could also store data on a hard disk or a tape. As we get to higher levels of the memory hierarchy, or lower rows in this table, accesses will take longer, but we can also store more memory there. So registers, we're storing at most maybe half a kilobyte to 3 kilobytes of memory. So not very much data at all. Primary or L1 cache will allow us to fit up to 32 to 256 kilobytes on typical processors today. So that's enough to store maybe the hottest sections of your program and data. There are subsequently larger caches that might go up to, say, 32 megabyte, whereas main memory might be from 1 gigabyte up to perhaps on large machines, a terabyte of memory. Certainly we can store more than this on flash drives, and tape drives have the largest storage with up to 30 terabytes per cartridge. When we program, only registers, memory, and devices, such as storage devices, are visible to the programmer as part of the hardware-software interface. Compilers manage those registers, moving data to them, to those registers from memory, and then back to memory once computation is done. The hardware manages caches to make access to frequently used parts of memory faster. So when we access a piece of main memory frequently, the hardware will move it to the cache for us. We don't have to control that ourselves as a programmer. Finally, devices are accessed by the operating system. Let's talk about registers in more detail. So registers hold very small amounts of data. Typically, one register will hold 1 word of data. So it's accessible very quickly, typically in 1 cycle, and most machines have different kinds of registers. Every machine has integer registers. Most machines have floating point registers in addition, and sometimes there are vector registers that allow us to do many computations in parallel, typically based on integers. There may be some special registers that are devoted to tasks, such as the program counter, which has the address of the next instruction that we're going to execute. The processor status register will also keep track of information like the privilege level. Are we executing inside the operating system or inside an application that would have lower privilege? What are What is the setting of interrupts and traps? Are interrupts enabled or disabled? And what is the status of condition codes that tell us where we might want to branch next? Caches are like main memory, but they're smaller and much faster. They hold recently accessed memory. So if you access a piece of memory, it will be loaded into the cache, and then if you access it again, that second access will be faster. There are multiple levels of cache because the smaller, the closer levels, like L1 cache, will be accessible very quickly and will be dedicated to a single processor core, so that L1 memory is very, very close to the processor, but it can only hold a little bit of data. So it's nice to have a second level of cache. An L2 level of cache might be on the same chip as the processor and might be shared by, say, 2 to 4 cores, whereas L3 would be shared by all cores. Each of these is, each level is larger than the previous level, but also slower to access because it's further from the core of the processor. Caches are loaded one line at a time in a cache miss. So a line is anything from 16 to 512 bytes. So we'll be loading several words from memory at once. This is useful when memory is accessed in order. We commonly scan strings or scan arrays in order. And so if we read a first byte of a cache line, then it's likely that we'll be reading later bytes of that same cache line. So we bring the whole line into the cache, and we can get performance benefits from that. Let's talk about memory and how it affects compilation. Because of caching, memory locality is important. Are we accessing the same data repeatedly in a window of time? That'll be good because that data will be captured by the cache, and we can reuse that same data, accessing more quickly in future times. It's also good to access data that's in the same cache line. So sequential accesses tend to hit on data in the same cache lines as earlier accesses. And again, that means that the work that we did to load the cache line into memory will be paid off when we access the whole line. Most machines require aligned access. So if we have an n-byte operand, we should store it in a memory address that's divisible by n. So for example, if we have a 4-bit integer, maybe on a word on a 32-bit machine, that should be stored at an address that's divisible by 4. In some cases, the rule is n over 2. So often doubles can be 4-byte aligned. The rationale for this is that it means we don't have to shift bits in our load path from the memory to the processor. We can just load the whole data as a chunk and not shift it left or right. So that simplifies and speeds up our hardware. It also can help with the instruction set. So in a fixed size instruction that includes an offset address, that offset could be specified in words instead of bytes. And so we can cover 4 times larger memory space with our bits available to specify offsets if we assume 4-bit byte word alignment. If you access a bit of some address in memory that's not aligned, on some architectures it might be slower, and in other architectures it might fault entirely. Let's check our understanding.